Well, welcome back, everyone. It's the final lecture for the entire course, so congratulations on nearly getting through 100% of everything. One thing I want to mention right away is I have gotten several emails this morning from pretty much all of my classes about the Pocatello Testing Center relative to scheduling the final exam. The Pocatello Testing Center has been struggling with their capacity, even though they're in the new complex. So if you're still scheduling your exam, and you look into the schedule and see that the only availability is on Friday, May 8th, I am allowing that to be a possibility to schedule the final exam since the seats filling up Monday through Thursday is something that's just beyond our control. So if you're a little anxious about that, you're welcome to schedule on the 8th, and they will accept your booking for that final exam. But any other questions about that or other topics at the moment? Okay, well, aside from that comment there, if you haven't scheduled your exam, please do so as soon as possible to get your preferred time. For the in-person section, we'll be meeting at this time, 12:30 to 2:30 p.m. And that's pretty much it for the course. We won't have any other meetings on finals week. But if you have any emails or any questions that come up while you're studying for the exam over the weekend during finals week, don't hesitate to email. I'll get back to you as fast as possible. I won't have office hours on finals week, but if you need to connect, just send me a quick email and we can make that a possibility. So yeah, the last week for the official office hours is our current week, but on finals week, the schedule gets completely just torn upside down. So let me know if you'd like to connect over Zoom, connect over email, and we can work that out on a one-by-one basis. Other questions at the moment? Okay, aside from that, the final assignment, section 8.3 is due today. There was no homework assignment from section 8.4, but like we mentioned, there's 3 examples there. I'm going to pick one of the 3, turn it into an extra credit question on the final exam. So if you decide to pursue this, I'm going to finalize those problems, post all the solutions. Once I get caught up on grading on Friday, I'll finalize any solutions that we don't get to here on this document, and then start working on that document as well. It's going to be a busy Friday of doing the same kind of things in all of my classes. So some of this work might spill over into the weekend, possibly Saturday morning. Aside from that, don't forget to check out the extra credit opportunities. We've talked about them a couple times, so we won't take too much time. The course evaluation will allow for a bonus extra assignment to be dropped. May 7th is the last day for turning in any work, whether it's a homework set from way back or maybe 8.3, that'll be the last official day for submitting work. But aside from that, we're just going to jump in. It'll be a problem and a solution day going on just from problem to problem. Any questions or comments at all, folks, before we get started? Okay, well, these are good sample final exams as well, but they're gigantic. Use these to target specific sections. This document here is just my way to convey what a real final exam is going to look like. It's not necessarily going to be the exact same questions, but it gives you an idea for how long, what kind of questions you should be expecting. So let's jump back in. We were working a little bit in set theory, and this is the problem we left off on Tuesday, writing down the power set of a set X indicated this way. To start this off, it's not a bad idea to have an expectation of how big this power set is going to be. So we can use a formula that says the cardinality of the power set of a set X is always 2 to the power of the size of X. X has 4 elements, so this is 2 to the power 4, meaning we're writing down 16 elements to get us started. Other thing to remember is when we write down this symbol, power set of X, that's the symbol for the power set. And power set just means the set of all subsets. So we begin by writing down a set symbol because it's a set that contains all the subsets. One subset is the empty set because the empty set is a subset of any set whatsoever, including itself. Now we start trying to organize. We need 15 more sets. So doing this in a logical way, is really critical for not missing a single one. Next thing I would advise is go for the sets of size 1, sometimes called the singleton sets. There's 4 of them: alpha, beta, X, and Y. You get pretty good at writing these curly braces. They're all subsets, so that means they're sets it sets in and of themselves. Sorry, I'm tripping over my words. So now we go to the next size sets of size 2. So of size 2, one way you could do is start with alpha and then pair it with the other entries down the line. So go alpha beta, alpha X, alpha Y. Then after we've paired alpha with everything else, you can move over to beta, do the same thing. Notice we don't have to put in beta alpha because order is immaterial when it comes to sets. That could trip us up. So that would be a duplicate entry. So we're only looking to the right when we're forming the next set of subsets of size 2. So we go beta X. That's not on the list until now. And beta Y is the next new entry. Then move over one element. The only set of size 2 that's not there is XY. That's supposed to be a comma. So here's XY. And we're definitely getting there. The next layer we're going to have to put in is sets of size 3. Now, when it comes to sets of size 3, because the cardinality of X is 4, a different kind of way to organize is pretty valuable. You get your sets of size 3 by deleting the elements one at a time. So here's how I'm going to do this one. Delete alpha to start. That leaves over beta XY. Then next, delete beta, and you'll get just alpha XY. Next, delete X. We have left over alpha, beta, Y. Finally, delete Y from this set. That's the last subset of size 3, alpha, beta, X. Then finally, X is going to qualify as a subset of itself. So we take the entire set of size 4, exactly one subset of that type. X is a fine way to notate it. And it's really easy to miss something, especially if this was size 5, but that would be 32 elements. I think that's just too much tedium on that level. Expect anywhere, say, size 3, size 4, size 2 if it's just meant to be a super, super fast problem. So let's double check. We have 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've got all subsets listed out. Well, any questions at all, folks? Power sets?
What's X at the end of the last set?
Oh, this X right here was just that X right there,
Okay.
the original set.
Okay.
And you could list it out as just curly brace alpha, beta, XY if you prefer.
Okay. And then why does the null set only appear once in the beginning and not anywhere else?
Well, if you wrote it twice, it would be kind of like, say, writing something like this: a generic set, A equals 1, 1, 2, 3. Interesting thing about sets is that the order doesn't matter. We can scramble them. But the next thing that's very interesting about sets is they are only meant to be including unique elements. So if there's a duplicate in my set, it simplifies automatically as 1, 2, 3. And so we always write it in most simplest form. So if you did put the empty set on the right, it wouldn't really hurt, but it would be a duplicate. The size of the power set is still 16, not 17.
Okay.
Does that make sense with that one, that concept there?
So we're just including the null set at the beginning of the power set because it's vacuously in the null set or vacuously in the power set.
Yeah, I like how you said that. The statement, empty set, subset of X, is vacuously true. And yeah, that's the only reason it's included there, but just once. Other comments or questions so far? Okay, vacuous truths, again, is one of the weird things about this class. It enters in a lot of strange kind of ways, and subsetting is one of them. But let's take a look into now the next concept. We're moving out of set theory into now chapter 3, dealing with logic. And this one's kind of a warm-up problem, but you should expect something like this, where all we're doing here is testing overall each one of these statements is true or false. Sorry, go ahead, Sophia.
Instead of just writing X, could we just write it out, or just to be
Yeah,
like
absolutely.
100% sure?
Yeah, you're saying write out as alpha.
Yes, exactly.
Absolutely. I'll leave it up to you how you'd like to format that very last set.
Okay.
So you could use by substitution X, but this flows better because it looks like all the other elements. Feels more logical, right? Now it's 4 elements,
Yeah.
definitely.
Yeah. Okay, thank you.
You bet. Other questions at the moment? Okay, well, let's give this one down below a try. These can sometimes be tricky, but I recall, I believe this was on exam 2, people did really well with this kind of concept. We're going to denote P, a proposition taking on a value true. Q, sometimes called a variable or an atomic proposition, is going to take on the value false. R is going to take on the value true. And we'll consider these just one at a time. So if we're looking into not Q and R, we need to be really careful with this one. This one is a conjunction, and we're only ever going to get a true if both elements left and right are true at the same time, or better to say propositions rather than elements. So negation of false, or excuse me, negation of Q, because Q is false, this one's going to be true. R is true. So we can say overall, not Q and R is true. Exclamation mark not required, but that's one down, 2 more to get through. So the conjunction's kind of nice. If it was the, say, or instead of and, that one is tricky in its own right because we could have had a false here or a false there. This one's quite tricky because we have to watch out for vacuous truths. We're going to look into truth tables after some of these problems here, so we'll look into implication a little bit closer. But let's say if we're going P implies Q or not R. Let's take a look at the truth values of these. P is true, and that means we have to work really hard. If P was false, we would just say true immediately, and it would be vacuously true. So the fact that P is true means we have to look a little bit closer. The entire statement here now has to be true in order to output a true. So let's look at to Q. It's false, but we can't make a final determination yet because we have a disjunction, an or statement in the middle. So false here. R is true, but that's the negation of R. It's false. Excuse me. That means with the or statement, false altogether because both sides are false. And in the implication, if you go from a true to a false, the overall statement is now false. So essentially all we're doing is thinking about what are the truth tables for and, for or, for an implication, a negation, and seeing if we can get a truer statement out if we had the completed truth table for that entire statement, which is what we're going to do in the next problems. Any questions with these first two? Okay, now we have exclusive or, biconditional. So these are new to this problem. So let's do this one really carefully. I feel like exclusive or, it just didn't get a lot of action in our course. I mean, we introduced it because it's important, but then we kind of left it off when we went to chapters 4, 5, and so on. So let's be really careful with this one. We definitely looked into the biconditional a lot. So let's maybe think about that first. A biconditional will output a true if and only if, which is what that is, the left side and the right side have the exact same truth values. So if I have true here and overall true here, the whole biconditional statement is true. If I have false here and false here, the whole biconditional statement is still true. So let's look into the simpler side. R is set to be true. So now this forces our hand. The overall complete statement is only true if the left-hand side is true at the same exact time. We must match the truth values. So now we go down the line, P is true. Now, because this is an exclusive OR, if I get true on Q as well, this whole thing is false. Exclusive OR says one is true or the other is true, but not both. So, hey, it's kind of nice. Q is false. So we have truth on one, but not both. So that means this entire compound statement true as well. The biconditional on the left side and then on the right side has the same exact truth assignments. So now we can say overall, the statement is true. So that's how to compute these. It's like looking at the whole truth table, but we're focusing on just one line where we had these particular values for P, Q, and R. If you gave the entire truth table to analyze this, it works too, but it's more computation that's necessary. Any questions or comments, folks, getting through this one? Okay, for the next problem, now we are going to break out the truth tables to see what's going on with these kind of statements. We're going to look into logical equivalence and also categorize this proposition according to whether it is a satisfiable. Let's put a bit of a review here. Satisfiable means true on at least one row. By row, we mean row in the truth table. Unsatisfiable means false on all rows. There's no way you can make this become true whatsoever. Tautology, this means true on all rows. So that's going to be our way to analyze this. This time we need the total truth table to determine this. Potentially, depends on how you like to analyze it, but I think that's the most efficient way for these problems. Break out the truth table rather than just picking specific assignments, true, false, and so on, for P and Q, is going to be much more efficient. As far as the truth tables go for the final exam, on homework and on exams and in the lecture, we did truth tables with 3 variables, P, Q, R. But I'm going to keep this a little bit toned down. We're just going to get right to the punchline with truth tables involving just P and Q to not make the exam too big. So let's start organizing this. We have a P for sure. I'm going to just put it in a long row to make sure we contain everything. Here's a Q. And looking at the left-hand side, it'd be valuable to have not P here. Personally, you could skip this, but for me personally, I'm more accurate if I put in the not P before I consider not P implies Q. Then there's an OR statement, but for the moment, let's focus on the right side across the OR statement. A not Q comes up, so let me put this in for just insurance on making sure I got my truth assignments right. Then look at the overall statement, P and not Q. And then going by a nice comment that I recall was made in class when we were first doing these, sometimes it's nice for our eyes to assign an overall variable to the 2 different sides. So let's call this P, let's call this Q. And the final column is we're going to take a look into P or Q. So I think that'd be a nice way to analyze this. We need 4 rows. Okay, so there's my freehand, got a little wavy there. And however you'd like to assign these values is up to you. I'll do the same thing that we've been doing since chapter 3. True, true, false, false. True, false, true, false. Then from here, we're just filling this out. We're going to compute these as we go. Let me know if you have any questions at the moment. Okay, well, as far as not P goes, we just go to the P column, flip all truth assignments. So false, false, true, true. And maybe another comment that came up in chapter 3. Some people like to denote these different ways. We had discussion about some people might use ones or zeros. Some people might use an element 1 to indicate true, blank to indicate false. All that's fine as well if you like to go that route. Just say what your convention is somewhere on the exam. You don't have to say it multiple times so that I know your meaning. I probably can infer it, but it'd be good to define it as well. And then I'm not too picky about how you notate this, but I'll copy the methods from the textbook just for the sake of consistency. So now we've got the not P. That means it makes sense to do not P implies Q. So we're going in this direction. Not P implies Q. We need to be really careful, but these are the freebies. Vacuous truth occurs when not P starts off as false. Automatically true on both of those, vacuously true. In the implication, not P implies Q goes from a truth to a false, and that is the one and only one way to get false. And that happens twice, true to false. Let me know if I flip something incorrectly or miscompute any values. But looks like we're done with that part. We can move over to not Q and do the other big chunk. Not Q just flips truth assignments once again.
I have a question.
Yeah, go ahead.
So in the third line, doesn't it say, oh, true, true with Q and not P? So it would be true, and then the next one would be false.
So Q and not P. So true, true here. You're referring to this spot right here, highlighted?
Yes, exactly.
Gotcha. So we're going from, oh yeah, thank you for spotting that. I was going from, or hang on.
I think from not P to P is what you were looking at, so it did make sense that it would be false.
Yeah, I think I was going from here out to here. Thanks for spotting that. So we should be going here to here. Good eye. Thanks for mentioning that, Sophia.
Yeah.
So if we're going from true to true, that's absolutely true. Thanks for spotting that. So true on this one. And we're going from true to false on this one. I was just lucky with that, right? So that does come out false, but that's because I was looking at that one. I should have been looking at that one. That one was just luck, sheer luck. Again, thanks for spotting that. Other questions at the moment? Okay, I guess the takeaway from this is be careful with the directionality and where your eyes are going, or if you're drawing on a paper like I did, where your arrow is going, because that can definitely mix us up. So let's try again. Same idea in mind. Not Q means specifically put your eyeballs there and flip those assignments. So false, true, false, true. So we've got the not Q down. And next, it's going to be P. So over here. And, so a conjunction, not Q. With the and statement, the moment we spot a false, automatic false will occur. So getting a false here implies false. False here implies false. We're only going to get true if we match up true all the way to true. So it works on this one for true. But if we go from not Q, true, we're okay so far. But clear over here is false. So we would get a false on that one. Okay, so far so good. A lot of columns, so it starts to get trickier as we go. But here's where the paraphrasing, just calling this a proposition P, proposition Q, starts to help our eyes, because now all that matters are these two columns here and here. It's an or statement, so the moment we spot a true, we get a true. So these are the three freebies, true, true, and with the correction there, true as well. Next, I have a false here, also a false here, through the or statement, two falses on either side would give us a false over all. So now, as far as we're analyzing for the overall question, it's definitely not unsatisfiable because the moment we have a true, that's off the table. It's definitely not a tautology because we found a false. Tautology means always true, but there's three ways to satisfy this, three different kinds of values that can occur. So we'll say it is, in fact, satisfiable. I'll say just briefly, P or Q, with the definitions implied above, is satisfiable. Then our work is done at that spot. Kind of a, again, weird way to compute things. It's kind of satisfying to get through them, but don't do as I did. Try not to rip through it. Be really careful as you go. There'll be plenty of time on the exam because those kind of mistakes highlighted in yellow are surprisingly easy to make. Any last questions or comments on problem 4? Okay, well, we have kind of 4 different classifications. The 3 we're looking into problem 4, but now as far as logical equivalence goes, logical equivalence means same, truth, assignments. In other words, we're going to say that the entire thing on the left will have the same truth assignment as not P. Or a different way to say it, logical equivalence is saying not P as a logical structure, a logical connective, is completely the same statement as P implies Q and P implies not Q. That's kind of a mind bender, right? This says it's a real logical equivalence. So we're going to see if we can prove this, that somehow P implies Q and P implies not Q. That's just a long way to say not P. So this is the simplification of that entire compound expression on the left. So the way we're going to validate this is yet another truth table. We have PQ to start. Let's just go long form just in case we need extra space. Here's P, here's Q. Now let's analyze what we need. We can do P implies Q pretty fast with just the P and Q columns. Next, it'd be valuable to have a not Q, so let's throw that in. And we're going to look into, after that, P implies not Q. Then this is a pretty gigantic compound statement on the whole left-hand side. So let's now chunk this up as P implies Q, P implies not Q. Give them new names. Let's call this P, Q. This time it's an and statement that we're joining. So we're going to look into overall what happens with P and Q. So that's a lot of columns already. But then the far right-hand side is no big deal. We're going to compare this column. I'll put a question mark. Is that column logically equivalent to that column, not P? Just has to have the same exact truth as statements. Let me fix that logical connective. That's the not statement there. So start off with your first row to kind of organize everything you need to compute rather. Let's start building out the table carefully. I'll try to be more careful than last time, but let me know this moment you spot something as just not right. So I'll go the same way as before. True, true, false, false. True, false, true, false. And this one's not too bad. We're going from P to Q. There's only one false right here. So if you go from true to false, you get that false. Everything else is some brand of true. So after we get that, negate Q. Those are always fun. Just flip things around. False, true, false, true. And here's the dangerous one. We're going from P implies not Q. We're going in this direction. So let me put that as a temporary assist for my eyeballs to make sure we get this one down right. We're going to true to a false. So that would mean P implies not Q is false on this one. Next, true to true, and the implication gives us a true. And these ones, we don't have to think too hard. These are automatic vacuous truths. So true and true. Okay, so that's the P implies Q side. Almost done with the table. We're now going to take the entire P column, the Q column highlighted, and see what these values are. But any questions, comments at the moment? Okay, now this time in our table, the big compound statement has an and in the middle. With that, the moment we find false, we'll just say false. So we have a false on this row. Another false on this row because P on row 2 is false as well. But on the remaining 2 rows, both here and here, they're all true. So we're going to get true with true. Okay, now let's take a look into negate P. If we negate P, we'll get false, false, true and true. And now we have done the proof. It said prove it really is a logical equivalence. So we were expecting the same truth assignments. False, false, true, true on both sides of the logical equivalence. So our work there is done. Let's make just an overall statement for the notes. Same truth assignments. This automatically implies the completion of our proof that using the same shorthand notation, P and Q, is in fact one really weird long form way to say not P. And I bet lawyers love that because if you have to say not P, but you want to confuse a jury, wrap the statement around this, and you can really put people through a spin on what you even try to say. So that's one, I guess, not the best application of logic, but that's something that possibly does happen sometimes. People have to untangle statements to see what did they really try to say. But any last questions or thoughts, folks, on this conclusion here? Okay, well, at this point, other things we're going to pay attention to in this chapter is nested quantifiers. I couldn't ask everything that we did in chapter 3, so these are the elements you see here on the practice exam that we're really focusing on. And this one I feel like is a good one to spend some time on because part C is the kind of tricky portion of this one. Let's go through it carefully. This is pretty similar to something we did in the notes, something you did on a homework assignment. But a problem like this, part C was not on exam 2, making it slightly tricky for that reason. I'll keep that in mind when I grade this on the real final exam, that it wasn't on a particular exam. But so let's still give our best try, see how it goes. So we have a statement, a predicate function, P of xy. P of xy is the overall statement that student X has taken class Y at ISU. Domain is going to be U for all ISU students, V for all ISU students. And because this is a true function, we can now say that P as a function mapping goes from U cross V to the set of Boolean values, true, false. You know, because it's a function on U cross V, in a certain sense, you could build a relation out of this. And this is how relational databases are built, using these kind of predicate functions, which intersects with the relations at the same time. But our job here is express each of the following statements using quantifiers, standard logical connectives, and the predicate function P all at the same time. So P is the major thing here we're focusing on. Let's do these carefully. When it says, there is a student, for the sake of notes, let's indicate the moment we said this, there is, it's like saying for some student, there exists a student. Any way we verbalize that, we are talking about an existential quantifier who has taken every class. When we say every class here, we can say that differently. We could say for all classes, the student has taken it. Either way, it's verbalized in ordinary writing. That's the universal quantifier for every. And as far as taken in class goes, we're using the predicate function. So to write the complete statement, we start with, if there is a student, we mean there exists some element, I'll call it X again, some element X in the domain U. The colon reads as such that, some people use commas, I'm not too picky on that, such that, taken every class, let's focus on every class first. V is all classes, so we'll say for all classes in the set V, all ISU classes. Now we go back to this one, taking the class means P XY. Now we mentioned this before. I think we really mentioned it a lot when we were doing, say, proofs by induction, that you don't have to say equals true here. You can if you like. That's being extremely verbatim, slightly redundant. It's implied that we are meaning P of XY is true when we write it out this way. So if you decide to put equals true, completely fine, and it makes sense. There's the Boolean valued function, and that's what we're trying to say. If you leave it like this, it's implied you meant it's true. P of XY holds as a true value. But we did it, folks. That's the overall write out for that one. Any questions on that statement there? Okay. Now, if we write out differently, every student has taken at least one class. All we're doing really is we're taking the quantifiers and flipping them around. Notice they're very, very different students. A student has taken every class is an exceptional person. That person has amassed a lot of knowledge. I mean, it didn't say they passed every class, but they've taken every class. That's kind of unusual. This one is interesting in its own right, but it's saying something different. Here, when it says every, that's the for all. At least one is the existential quantifier. So if we write out this one, we're going to say for every X in U. Taken at least one class means there exists at least one class Y in the set of V of all classes such that P of XY. Again, very, very different kind of statement on this one. If we had to negate any one of these, let's negate one of them just for the sake of practice. The negation is done by flipping the quantifiers again. Negate this statement and you'll have exists X in U such that for every Y in V, negate that, we would do it in this way. You could say PXY equals false. That's a completely fine way to do it. I think the more typical way, the way we did it in class, was negation of PXY, which means now we're saying not P of XY is true. So that's what the negation would look like. Don't forget the not operator there. So this one's saying there's at least one student that for every class, they haven't taken it. One student that has not taken any class whatsoever, yet they're still registered, they're hanging around, they don't want to take any classes. That seems kind of weird, but that's what the negation would be. Well, any questions whatsoever, folks, with the part A or B? Okay, so this next part is kind of the mind bender in this problem. I'm not going to ask you to write a lot of pseudocode on the final exam. I feel like we've done plenty of that in the applications. So this is going to be the one spot where you're writing pseudocode. There'll be one other spot where you're going to trace pseudocode. So let's do this really carefully. Let's think of what our objective is. Write pseudocode that checks if the statement in part B is true. What makes this kind of a mind bender is we're seeing information three different ways. An ordinary English statement. Every student has taken one class. Now in pure logic with a predicate function on a complicated domain. And the third way we're going to see this is, what does it look like as pseudocode? So all of these things have to come together. We want to have our pseudocode output a true if the statement is true. So our pseudocode is going to use nested for loops for each one of these quantifiers that came up. Let's start with going left to right. For x in u. I'll use the curly braces. They're not completely required, but for my eyes, they track a little bit better if I see the curly braces. Now, what's our objective? We're trying to see if every single student here has taken at least one class. The first thing we want to initialize is another dummy variable of some kind. I'll call it just generically taken class, and we'll initialize it to a value false. Now let me write in a comment. Our objective here is to see, can we flip this one to true on every single student? So if we can find that class that the student has taken, flipping that to true on every single student, our job is done. We'd write the pseudocode that checks if this is really true. So my brief comment would be along these lines: try to find a class. We're already going to grab a student, and we're doing this for all of them. Try to find a class that flips this to true for every student. So that's our objective. So now in our loop, we now need to nest our loops and loop through all of the potential classes, trying to see if that student has taken class Y. So this is our next level of the loop. Let's write for Y in V. Now we're grabbing all the classes, we're matching it up with the particular chosen student X, and we're dropping it into the predicate function just to see what's going to happen with the output. If that comes out as true, I want to flip that to true because we found a match, a class that the student has taken. So this is really an if-then statement altogether. So let me indent again. If pxy I'll use kind of lost my words on that. I'll use the way to double check if this is an equivalent value on the left to on the right. So if it's completely identical to a comparison check, I think that's what I was trying to say. If pxy is completely equal to true, that means we get to take this thing right here, taken class for that particular student, is true. So if that's the case, we're done with that student. We're just going to go off to the next one. You could optimize your code a little bit, because once you find one class Y that works, you don't have to check every other class. This is going to just stay true, and you're going to constantly reassign true for every new class that comes out as true. So if you want, you can say break here. Close the if statement. This is going to break out of the entire loop that's job is to check all the classes. And so that's the conclusion of this loop. We're still not done with the pseudocode, but any questions or comments to this stage? Okay, so it's a good idea to kind of think through this every time we work through it. Let's refresh. We're trying to see if it's true that every student has taken at least one class. So we're going to check across every student, the first quantifier. We're trying to find one class. Here's the second for loop for the second quantifier. If it checks and comes out as true, great. But we have to say, what if that never flips to true? what if PXY is always false? We found a student that hasn't taken any class whatsoever. So let's write a condition for that. If taken class, let's do a comparison check. If this is identically equal to still false, we never flipped it to true. We never found a class that matched up with that student X. Then we're done with this whole thing. If we find one student that has not taken a single class, the whole statement is false. So we're going to just say return false. This is what our pseudocode is going to output. And on that return value, we're not even going to loop anymore on the outer loop. As soon as one student comes up where that stays false, we are done. The whole thing is going to terminate with a false return. But then we have to imagine, let's suppose it really is true. We're starting to loop through all the students. We go through here. This might come out with lots and lots of falses until it hits the first true. It flips to true. We break. This never runs because we found a match, a class that the student has taken. So we loop back. We go to the next student. We reinitialize to false to see if it'll flip to true. We keep on finding a new class, so we keep on skipping this. And if we keep on skipping this forever on every single unit in the set of all students in U, then this will never run, and the loop is done. We never hit there. We're never going to return false, but that means it's because this was true. We matched a class to all students. So after this for loop terminates, with that closed bracket here, that curly brace, we will just say return true, because now we verified the code did manually that every student does in fact match up with some class. So this is a true statement overall. For me, this is pretty tricky. I feel like every time I try to look at this, I need to convince myself it's right by thinking through it, tracking through, imagining the computer looping through values. Sometimes it takes a moment to convince yourself of this, but any questions or comments at all getting through it? Okay, so again, there won't be a lot of pseudocode writing. Expect something along these lines. I think this is a good thing to try to expand on our knowledge on what universal quantifiers are like these are really trying to say by going from an English statement to the quantified statement to building a procedure, the actual pseudocode that ties back to that. So that's going to be our major work on the quantifiers for the final exam. Beyond this, we're now looking into proofs, proof techniques. So let's scroll off to the next portion. And while we're thinking about pseudocode, like I mentioned, there'll be one problem where you're going to trace pseudocode. And that'll be this problem right here. This one's a slightly longer trace, but not too different than what we've done in the lecture notes, what you've done on the exam. And because we're getting kind of low on time, let me know if you all would like to jump to any problem whatsoever. All the problems I have here is the multiplication table for Z7 to compute inverses, drawing a directed graph on relation R on a set B, and proof by counterexample. I'm going to have show up in these kind of situations. I'll give you a relation and show it doesn't match up with some certain properties using the proof by counterexample technique. So that's about similar to what you're going to see on the real exam. It's not going to be a super long one, just kind of a representative selection of problems throughout the course. So here's the next ones. If we're going in order, again, let me know if you'd like to change the order at any point. Feel free to interject. Next one, we're going to give a direct formal proof by contrapositive, and after that, we'll do a proof by induction. Any questions at all before we start? Okay, let's give this a try. There's lots of proof techniques. So it could be a proof by contrapositive, proof of a biconditional, proof by cases. And as far as induction goes, I'm only going to ask one induction problem. I randomly selected whether it'll be standard induction like we see here or strong induction. I'm not going to involve pseudocode with the strong induction. It'll be kind of similar to the standard problems using with recursively defined sequences that we did in the lecture and the homework. Okay, let's start off with this one. If we're going to give a proof by contrapositive of that statement, we need to say what the contrapositive is to begin with. The contrapositive flips the if-then connective. Again, you could re-visualize this as just a statement, n squared is even implies n is even. So same verbatim kind of statement. We're just using the operator there to convey the implication. So this is the hypothesis on the standard statement. That's the conclusion. In the contrapositive, we make the arrows go the other way and we negate. So we start here and we say n is even. Here we've negated the statement of, hang on, we didn't negate anything. Let me backtrack on that. Negation of even ought to be odd. So let's start with n is odd. Implies n squared negates even again, odd. So that's our contrapositive. So essentially, we took this, negated it, it's now the left-hand side. We took this, negated it, and now it's the right-hand side, the conclusion. Once we have that written down, we can run through the proof. We're giving a formal proof, so we have to define all variables that come up. We have to quantify them in some way. We'll start with proving a standard implication. A direct proof would be assume that part is true. So we must say assume n in z is odd. So we have an odd integer. Now we need to say what this means. If n is odd, you can use the exist statement. Exist k in z. This is how we typically wrote it. Or you could say differently if you like, then n equals 2k plus 1, where k is in z. You could just write it out if you like. You don't have to use the existential operator. Ordinary words does just fine. But this is how we typically did it, so let's copy how we did it in the notes. Assuming n is odd, then this means there exists k in z, so we can pick out an integer such that n equals 2k plus 1. So that gives us odd. Once we have that down on paper, we can now say we have that for odd. Next, let's take n squared. With n squared, we can make a substitution, 2k plus 1. So that's, there goes n once again. Expand this expression and we'll get 4k squared plus 4k plus 1. We want to write it in that format, once again, with a different value for what k is at that red dot. So to start, factor out a 2. We have the 2 in front that we require. We're only factoring from the first two terms, so we're getting a 2k squared plus 2k plus 1. So that's our new value k. We should make a statement here just to be sure we didn't do anything weird algebraically, like say if that was a cube root for some strange reason, or we divide by 5, we've got a problem. We have to prove it's an integer. But here, no problems at all. We can just make a direct statement. Since 2k squared plus 2k is automatically an integer because k was squaring it, doubling it, adding double k again, doesn't change that fact. We have closure upon multiplication, addition, exponentiation on integers. So that's the short statement. It's back in the set z. We have n squared is odd. That was the conclusion we had to show. We started with n is odd. There's the format algebraically. We ended at this new algebraic format, where that part here is an integer, so still 2 times a different k value plus 1, giving us oddness again. So at that stage, you can make a statement, the proof is now complete since n was arbitrary. But if you end it right there, you've shown the final conclusion. N squared is odd. So if you want to make it a little short, not a bad idea for a timed exam. That's a good stopping point. Well, next up is induction, but any questions at all, folks, with that direct proof there? Okay, maybe saying a little bit more words on this. We proved that the contrapositive is true, and we are taking for granted that if you prove the contrapositive is true, the original statement is true as well, because they are logically equivalent to each other. You don't have to say that on the exam. We said that quite a bit on the notes just for connecting those ideas. So the statement is that you don't have to say each time is that P implies Q is in fact logically equivalent to not Q implies not P. But we take that for granted in a proof by contrapositive technique. So now let's skip on over to induction. I'm not going to give anything too fancy. I think you can expect something along these lines, a summation type of a problem, or possibly a recursion type of a problem as well with an infinite sequence, but I'm not going to involve any pseudocode statements. I think we did hammer that out pretty well in the third exam. It says first, define the predicate function P. So let's say, I'll go briefly, P of n. Don't forget your input n here because it depends on some input. It's a statement. We don't put equality. We just put a colon. P of n is the statement that. Take this and you can use it in that expanded form, but it is far more convenient algebraically to use summation notation. So I'm going to rewrite this as index I going from 1 to n, summation of I, that's the entire left-hand side, is equal to n times n plus 1 over 2. So that's our predicate function P. And our hope of hopes is that this is always true for all integers n in the right domain. So that's what this step is all about. Write the statement above. In terms of P, which you defined using quantifiers, means it needs a domain of discourse. So we need to say for all n in the set Z, but we must be careful, right? If you say it like that, you're implying negative integers, possibly 0, but the index starts really at 1. This is a formula that begins if you have 1 term, 2 terms, and so on. So some way we need to notate, we mean starting at 1, all let's say all positive integers would be a fine way to say that verbally. So for all n and z, P of n is true, and that's our short form of saying that. So there's our predicate function, there's our quantified statement. Major reason that we did this a lot in the lecture and the homework was when you take a look at the formulas provided on the real exam for induction, strong induction, they're all in terms of a predicate function P. So if we really want to track through the process of induction or strong induction, it is powerful to write P down on paper. So I found putting this down helps out a lot. We're usually a lot more accurate, able to get through the problem, track through the definition of induction. Now we need to prove a base case, which means we're going to the minimum element of that domain of discourse, say let n equals 1, and seeing if this statement is based in some truth. Is the base case when n is 1 true? If we plug 1 there, will we get a true statement out? Said differently. So we're just verifying if this is true when n is 1. Let's say then summation as I goes from 1 to n of I becomes summation as I goes from 1 to 1 of I. That's allowed in summation notation, even though it looks odd. That just means you're plugging 1 in for I, and then you stop. So that's the left-hand side. Then do it again for the right-hand side, n times n plus 1 over 2. We set n as 1, so that's still in scope on this line here. It becomes 1 times 1 plus 1 over 2. It simplifies back down to a 1. And that's good because now we have validated the left-hand side, the right-hand side of that equation there is in fact true. In other words, said differently, P of 1 is true. So that proves the base case. Don't forget to show all steps that shows that P of 1 is actually true. And don't forget to write out an overall conclusion. Any questions at all, folks, with that step there? Okay, now for the inductive case, we need to be very, very specific on our domain. It's anchored in whatever we said the domain of discourse is. We start at 1, then depending on the way you would like to prove this, and in the homework I saw really 2 different styles. Half the class said Pn minus 1 is true for their inductive hypothesis, and about half the class when I graded homework said P of n is true, and they proved P of n plus 1 is true on the inductive hypothesis. In my solutions for the notes, I went the same route there just to convey that's an appropriate way to go, but it's going to be completely up to you. I'm going to copy our author's definition to the letter and assume Pn minus 1 is true for my inductive hypothesis. But again, either way that you like to do it is 100% completely valid. It gives you the same result. Algebra looks a tiny bit different, but there's really no optimal choice. If we set n as 1, using our author's method, we need to now say, let n be greater than or equal to 1 higher. We increment by 1. Assume Pn minus 1 is true. We plug in the minimum value, that's P at 1 is true, and that's where we anchored our first truth in the base case. So that's how you can validate that you picked the right index. At the minimum value, when you plug it in, it has to tie back down to here, where your base case lived. Now, once you assume Pn minus 1 is true, we should make a statement just to help out with the flow of the logic, the algebra. This means we're taking n minus 1, we're plugging it in here, 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 and here. It's a really good idea to write down the predicate function again to show exactly what that looks like. Pn minus 1. Oh, I already wrote that. Pn minus 1 is true means we go back up to here rather. Summation I equals 1 to n minus 1 in that spot of I becomes n minus 1 times n minus 1 plus 1 over 2. So this will just be n minus 1 times n. You know, just for the sake of being completely complete on this, let me simplify that down. N minus 1 times n over 2 is true. So we can take that equation 100% for granted. It's assumed to be true through the inductive hypothesis. If you didn't write that down, but you use it, that's okay. Their proof will flow well, but we need to say this part right here, the inductive hypothesis, and we need to say specifically for what value of n. Now that we've done that, the next thing we're going to do is go back to the predicate function. And now we want to show that this holds at n as well, as a direct consequence of the inductive hypothesis. So if we can prove this equation now, our job is done. So here's our final steps. Usually we say something along the lines of next. Take summation, I goes from 1 to n of I. We need to land there. And our typical trick, whenever we dealt with summation notation, was we want to bring in the inductive hypothesis. We can sum up to n minus 1 in this way. Take a sum as I goes from 1 to n minus 1 of I, plus, if you've gone from all the way up to n minus 1, that means your last values when the index I goes up to n. It plugs in there, and then you're just adding n altogether. That's just the final n right here, if in the expanded form. But then once we have this on paper, that's where the inductive hypothesis plugs in. So this becomes n times n minus 1 over 2 plus n. I don't know why I color coded in that weird way. Let me fix that. So there's a substitution from the inductive hypothesis. From here on out, it's all just a bunch of algebra. We could rewrite this as n times n minus 1 over 2 plus 2n over 2, getting the least common denominator. Now we can expand n squared minus n plus 2n over 2. I've expanded and added across numerators. Combine like terms, and we have n squared plus n over 2. And we can factor next, n times n plus 1 over 2. But now this says, thinking in terms of equivalence classes, equality is an equivalence relation. Because it's an equivalence relation, we have transitivity of equality. From way over here, we can loop all the way to this statement and say, those n's are also now equal by transitivity of equality. That proves P of n is true. And you can just say the proof is complete right at that stage. You can end it in any way you'd like. Here's a kind of a satisfying way to end this. This shows for all n in Z bigger than or equal to 2, wrong spot, because we said that this is going to hold for an arbitrary n bigger than or equal to 2, P at n minus 1 implies, we just proved an implication, it implies that P of n is true. So we just proved that the entire implication statement here holds, but it held for any arbitrary value n, 2 or higher. So like dominoes, once the base case is proven as true, once we take an arbitrary value and show the implication here holds, this holds for every n in the domain of discourse. So this completes the proof. Well, we did it, folks. That's the end of this one. And again, proofs are not going to be a big part of the exam. It's going to be something along these two kind of problems. So expect one like this, where it's going to be induction or strong induction. One like this, where it can be just a direct proof, proof by contrapositive, a biconditional proof, potentially proof by cases would be the ones here. The last proof method is going to be proof by contrapositive, or excuse me, proof by finding a counterexample. But those were the kind of problems we were doing in that last section, 8.3. Well, we're kind of low on time, but any questions before we go off to the next? Okay, well, let's see what we can do in that time we've got. This one is kind of a fast one. Problem number 10 is a trace where we're going to do a recursive call about 4 layers deep and then have to unpause on line 5 several times to get back to the result. It looks like this one we won't be able to get through, but I'm going to type out the result to show exactly what it looks like when I get completed with grading on Friday. Beyond that, we have a multiplication table, and we can do either a directed graph or proof by contrapositives. Anyone have a preferred direction to go? While we're thinking of that, this one's pretty fast. Let's give this one a try. This one is just the division theorem, sometimes called the division algorithm. We're trying to find integers d and r such that n equals kd plus r, where r is strictly between 0 and less than k. So if you see a problem like this, pretty much all we're doing is taking n mod k. If it's n mod k, that means we're taking 23 mod 6. And that's pretty fast. We can write down the formula as we've done quite a bit in class. Up to you how you'd like to indicate this. 23 mod 6, well, 6 goes into 18 three times. It looks like this would have a remainder of 5. If you go this route and you don't use the formula, the next thing you do want to do is write down the floor of n over k. That's using the formula regardless, so just make sure you write that out. It's part of what we need to find. The floor of n over k is going to be the floor of 23 sixths. But the floor of 23 sixths would be 3. Doesn't hurt to double check in the calculator. 23 over 6 is 3.8, so the floor is 3. But whenever you're dividing like this and you're doing the floor, that's just how many times 6 goes into 23. That's the quotient. That's the remainder after dividing 6 into 23. So this gave us both elements we want. I don't know why our author calls this D. Maybe it's because we're dividing. Usually we think of that as the quotient, but it'd be weird to change the notation right now. So let's keep with that. In this division theorem, this is denoted as R. So we now have a value for R, we have a value for D, and our work is done right at that step. You don't have to say anything further, but the check on our work is so rapid, it's worthwhile. That is the check, n equals kd plus r. Verify that your value of r is strictly less than k and 0 at minimum. Yeah, k is 6, so it makes that hold there. So if n is 23 and k is 6, d is 3, r is 5, this says 18 plus 5, that's in fact 23. So that's the division theorem in a nutshell. That got involved with a lot of other algorithms down the line. Like say, for example, extended Euclidean algorithm got involved with this. But any questions at the moment? Okay, as far as this one goes, you'll do a trace of this particular algorithm. And I think that's a good hint to give because it sometimes can be a bit of a beast to get through. It's one of the reasons my exam is not too long. This one takes some careful analysis, but tracing code like this is an important objective for our course. So be careful as you go. Practice again with the one you did in the homework. Double check the one that we did in the exam and the sample exams to be prepared, and just take your time with it. When you get to the very end, do a check like this because it's really fast to verify if you made a mistake somewhere. The check is this part right here, r equals xn plus ym. So again, I'll write out the full solution to this trace here. And for the time we have, it looks like we're kind of out of time to do a complete problem, but just some quick comments. This is another one we did in the lecture and the homework problems as well. Don't forget it's kind of a two-part problem. Once you complete the entire multiplication table, look for the ones, and that'll tell you where your inverses are going to exist. For the directed graph on this one is kind of fun. This was in the homework in section 8.3. This one's a pretty fast problem, so this one won't be too major. But be ready to go for counterexamples. As far as the counterexamples go, take a look at what we did in the notes, what you've done in the section 8.3 as well. This one can be a little bit trickier than intended, so I'll keep that in mind. This was the last homework set of the entire course. So give it your best try. It's a proof by counterexample on every single one of them. And I'll show how these go once I get some time to finish off the notes. But any last questions or comments whatsoever, folks, before we call it a day? Okay, well, have a great afternoon, folks. I hope the studying is going well for your other exams. And again, if you didn't catch the message that we were talking about earlier at the start of the class, the Pocatello Testing Center, probably due to some staffing issues, has completely filled up from Monday through Thursday on final exam week. So if you're forced to schedule on Friday the 8th, we don't have any recourse. You're absolutely welcome to do so. So don't feel bad if that's all you see left over there. Well, if you have any questions whatsoever while you're studying, don't hesitate to reach out. I'll be checking my email every day throughout the weekend, throughout finals week, and I'll be happy to work with you. But have a great afternoon, folks. Congratulations on getting through the course. Just one more last formality to get through.